Well, good afternoon and welcome to Bulldogs Behind the Scenes, where we delve into the people, places, and research connected to the University of Minnesota Duluth. Today, we are excited to explore a fascinating course at UMD that focuses on the history of structures. Before we dive in, let's take a brief pause here to allow everyone a moment to log on. Well, my name is Molly Clevin, and I'm part of the University of Minnesota Duluth Alumni Relations team. Today, we have the pleasure of taking a behind-the-scenes look at the UMD class on the history of structures, led by Dr. Andrea Schocker. Before we begin, I'd like to highlight some of our past programs. We have explored places such as the Minnesota Landscape Arboretum, Amsoil Arena, the Superior Hiking Trail, the proposed UMD Sales Center, the UMD Chocolate Lab, Romano Gym, and many more. You can access all of these events on demand on our website at d.umn.edu/alumni. Today's webinar is being recorded and will be available on our Alumni Relations website. You'll receive an email with the link once it is ready. We'll also have time at the end of the presentation to answer your live questions. To submit a question, please use the question and answer button on the bottom of your screen. Now it is my pleasure to introduce Dr. Andrea Schocker, who will be guiding us through today's presentation. Dr. Schocker is a professor of civil engineering at UMD and has served in various roles, including as Executive Vice Chancellor for Academic Affairs from 2012 to 2016. She began her academic career at Penn State University and joined UMD in 2008 as the founding department head of the Civil Engineering program. Dr. Schocker is a licensed professional engineer in Minnesota with expertise in concrete structures, specifically low-carbon concrete, structural resilience, and segmental post-tension bridges. She has received numerous awards for her teaching, advising, and initiatives to support women in STEM fields. In her personal life, Andrea and her husband have one son who is a college freshman and 4 dogs, which she enjoys showing in her free time. It is now my pleasure to hand it over to Dr. Andrea Schocker.
Thank you. It's great to be here. I'm excited. I think we've probably got some folks online who are alumni who might have been in this class and other colleagues and alumni. So my goal today is just to give you a little bit of information, both about kind of how this course works, some of the details behind the scenes, and then give you just a little sample of what I would cover in the typical course. So this opening slide, I think you probably recognize some of these structures. This is, of course, the Eiffel Tower on top, and on the lower right, the Golden Gate Bridge, and on the lower left, an early version of our Duluth lift bridge before we actually had the lift span. So I am a civil engineer, but my specialty is in structures. So a lot of times in civil engineering, we will designate our specialty area. So I'm a structural engineer. Civil engineering is actually the original engineering type, and it covers multiple areas, including transportation, water, environmental, geotech, and a lot of other things. And so what's remained as different branches have moved on to mechanical or some of the other areas. And so I do specifically concrete structures. And we'll get started here. So this course is really a different type of engineering course. It's not going to be one that you would typically encounter in an engineering curriculum. And I've sprinkled different pictures from the course throughout here, but I'm not going to spend a ton of time on the details because we just don't have time to go into that. So our objectives, it's always good to start out with some objectives. After the talk today, what I hope is that you'll be able to describe the role of structural engineers in society. And then I'm introducing you to the concept of structural art and structural artists, which are our engineers. And we are also going to look at some of the unique educational approaches that I have for this particular course. And then here in gray is an important one that is just part of my personal mission, and that's to make sure that everyone in the world that I talk to knows the difference between cement and concrete. And so people who've had me for class are now laughing because this comes up a lot. So here's my public service announcement. Concrete and cement are not the same thing. Cement is a small component, or it's an important but small component of concrete mixture, which includes the cement, the water, some air, sand, and gravel are the aggregates. So very important that you leave today with that fourth objective taken care of. So we just start right off with it. And concrete's the hard stuff and cement's the powder. So there's not a cement sidewalk, there's a concrete sidewalk. There's a concrete slab in your basement. It's not cement. So it's similar to a cake is not just flour. So keep that one in mind and spread the word for me so I can continue on my mission with the differentiator here. So let's talk about this course that I teach at UMD. This is the history of structures. This is the wordy part. This bridge in the background, by the way, is in Hawaii, and it's a bridge that we did a little bit of work on, a student and I, and it is kind of in my specialty area of concrete segmental bridges. So this course, if I just look at the course description in the catalog, I'll point out a few keywords, and those are that we look at structures of historical significance over a long time frame. But what's unique here is that we're going to look at the social and economic importance, so the societal impacts, the merits of the engineering design, and I spend a bunch of the course talking about the actual the structural engineers who designed and in many cases supervised the construction of these unique structures. You, regardless of your background, kind of learn some basics about how load is transferred in a structure. In other words, how does the load from the cars and the bridge in the picture get down into the ground? What is that flow of forces? Now, it's qualitative, so we don't go through a lot of numbers in this course. It's really a conceptual type of course. And we look through many of the contemporary structural designers as well. And you'd recognize some of these names, such as Eiffel, who actually did a lot of bridges before doing the Eiffel Tower. Eads, Amman, Maillard, you may not know so many of those. But this takes us all throughout time. And I end up this class with a piece on ethics, taking a look at how to, there's more to a structure than and just carrying the loads. Is it cost effective and some of these types of things? One of those is a fairly controversial lecture about an architect, so you'd have to take the class to know about that one. So I won't talk about that a lot more today. But we also end up talking about some Duluth structures at the very end of the course. All right, so this course, this is a 1,000 level course, which means there's no there's no prerequisites, and it's intended to be a first level course. It's part of the liberal education curriculum, which is a little bit unusual for an engineering course. It has engineering as its backdrop, and it's kind of at the core, but at the same time, it has it contributes to the humanities and global perspectives category of liberal education. So the humanities part is looking at the social component, the historical component, and then I jump back and forth, but start at overseas in Europe. And as we develop the different structures, move across the globe. And because we're looking at those perspectives in a global sense, it also covers the global perspectives curriculum. This is a massive course. So this is an asynchronous, which just means that it's a go at your own pace to some extent, but we don't have live lectures. We have recorded videos, kind of like what we're doing today, that you can do at your own time. So that's the asynchronous online part. And the last couple times I've had over 600 students from all kinds of backgrounds. The students who've had me for a class other than this one know that I tend to be really into giving you case studies and stories on the spot, so the distinct organization and kind of rigidity of how I lay this course out is a little different than what I'm used to. But I will tell you, with 600 students, if I have 1 minute per student, that's 10 hours, just to give you an idea. So when I make a mistake and don't post something correctly, I get a lot of emails. And so I've learned to discipline myself and make sure that the organization of this course is good and that I make as few mistakes as possible. Part of this is also making sure that the outline of this course is really easy to follow so that there's no confusion in how you approach getting to the material. So I'm going to walk you through a little bit on this, how this course is laid out so you can get an idea. In case you were wondering, we hear a lot about, oh gosh, it's asynchronous or it's online. We don't like online. I do a survey at the end of each semester, and I've done this since I first started the course, asking them some specific questions about how the course is taught. And I think the summary here is that you can do a good asynchronous online course, and sometimes there's really good reasons for it. For instance, I started this one when it moved online during COVID. We were in a big lecture hall. It was a face-to-face course with over 100 people. But when we had to move online for COVID, what I realized was I was able that following semester, the number of students in my course, because the time was flexible and because the seating was not a limitation, blossomed into, I think, 350 that first semester, and it has gone up from there. So because of the way I offer this course and because it's easily adapted to this type of learning style, I'm able to make it available to a lot more students than I usually would. So I think my son and I are figured out at one point that basically 10% of UMD students have taken this course, and that continues to grow over the course of the 4 years. So my little survey here shows that in this case, for this course, when I asked them, what's the best way to offer the course as we move into the future? And there's other questions around how they liked it. 80% or close to 500 people out of the 619 that responded to the survey, 80% are believe that the fully asynchronous is a good option. And I'll talk to you a little bit about how the students often tell me they handle this course with the rest of their course load. So let's just take a snapshot from that survey of who's in the class. So this is my most recent survey this spring that we just finished up. And you'll see that I've got about a little under half are first year students, and it kind of goes up the line. But I have students from every year, and I have students from every college or every discipline area in at UMD. So part of this has changed over the years. It used to have higher percentages at the upper levels, but now a lot of those students have taken it as they come in. And so it's typical for me to have this course with a good number of first year students. And because of that, I format it to assume someone just walked in the door and to help them have a successful experience in possibly their first real online course, one of their first courses at UMD, et cetera. Who's in the course? It's not all engineers, and it's not, but there are engineers in it. So if I take a look, as far as colleges go, I have a lot from each of the colleges. I have a good sampling. Business school is particularly popular. I've got 21% just from the business school. I think that that's a couple faculty I know in the business school who suggest this to the students. There's also a lot of word of mouth in the sciences of some of the students taking that, but we have everyone from the fine arts, liberal arts, and then in my own civil engineering department, we have a large number of students who take this, mechanical, et cetera. I will say that this course, because it doesn't have any prerequisites, I have to really think about how I organize things. So a civil engineer who's going to focus in structures should have the same ability for success in this course as someone who's in the arts or in business or any of those things. Likewise, a civil engineer who hasn't had any engineering courses yet would be in the same boat. So how do I do that? I'm going to talk a little bit about that shortly here. Okay, so this course, the student learning outcomes for this course, there's quite a few related to humanities and global perspectives, but of the course on a whole, my goal is for the students to understand how historical and cultural factors have shaped structures up into the modern times, and then understand some fundamental engineering considerations without getting into the math piece. So really the conceptual piece of this and some real basic math. And just to appreciate structures as an art form. Okay, I want students to leave this course and start to look around them, look at their environment, look up at the bridge, look at the structure, look at the building in a different way than they have before. I want them to understand how structural engineers impact our society or engineers in general. To have some basics, because as you go out and what's the importance of our infrastructure? When we're voting on funding for infrastructure, understanding some of that importance as a citizen. But why did I personally decide to teach this course? So it's a couple fold. I think education of all of us, regardless of our discipline, beyond just our narrow focus, is really important. And I really want to share what we do in structural engineering because it has such an impact on all of society. And it's really fascinating to look at both the historical and social and economic pieces of this, as well as the artistic piece of this. A lot is attributed in my discipline to architects, but structural engineers actually are significant players in this, particularly in the bridge world, where we are often both the structural designer and the kind of architectural structural art person in this. And then I also have, I was lucky to experience the person who kind of started this discussion around structural art. And that's David Billington, who has passed away, but he was a professor at Princeton University. And he was more on he's an engineer, but he also was fascinated by just architects and architecture as well. And I was fortunate enough to be organizing a conference where he was a keynote speaker and I had to help him set up. And this was in the days of slides. And so he wanted 3 screens going and he had a big long pointer stick and would smack that. And I mean, it was a stage show. And it was so exciting. It was like the dinner presentation. So it was a mixture of engineers and other audience members who weren't engineers, families and things like that. And it was just captivating. And I really wanted to, first of all, I wanted to be able to do what he did as far as teaching, but I also wanted to be able to spread knowledge the way he did. So his format has been carried on by a Professor Garlock at Princeton, but in a little different way. So I've developed using some materials from David Billington and Maria Garlock, as they did an NSF project that allowed some of this to be shared. But then I have developed it quite in a little bit different path based on structural engineering specifically. I also happen to know David's daughter. She was a classmate of mine when I was a PhD student. So lots of really cool connections, and I'm honored to be able to carry on this tradition. You can get his book. It says The New Art of Structural Engineering, but it's about 50 years old at this point. But some really cool, approachable stuff, even if you're not an engineer. All right, let's take a quick tour of the course. So as I was talking about, it's not a traditional engineering course. When a civil engineer or structural engineer takes this course, I want them to look at the appreciation and social and other and artistic piece. When I have someone who's in a different field who maybe already appreciates the artistic piece, I want them to see that in the structure, but I also want them to have a little bit of understanding on some of the engineering principles that go behind this. So this would be our landing page for the course. And you can see I can click in, know exactly week by week. And this course, my other courses are structured slightly different, but this one is specifically tailored to be online so that you can find things. And so this is a landing page. From there, they would go to what we call the modules, and those are just sections on topics. And in this particular course, it will give you week by week. So there's never any question about what's happening. And, if it's the week of January 16 and 19, I know where to click. I've closed up the drop downs here, except for one. But for instance, week 3, we talk about Roebling and the Brooklyn Bridge. And to progress on to the next module, the student has to check off that they have done those pieces. It is labeled very clearly step 1, 2, 3, so you know exactly what's happening. And each module is identical in how it's structured. So I think this organization piece is critical into a student being able to navigate this course, because they have to navigate this on their own, essentially, since it's asynchronous. They can always contact me, but they really need, my goal is for it to be really clear to 600 different people exactly what to do as you navigate the course. So it actually starts out with an intro module where I, in short video snippets, take them through the syllabus. There's a very detailed syllabus on the expectations I have for them and that they should have for me, how we should communicate if we need to communicate by email or office hours. And then I also walk them through how to navigate this course. At that point, all the expectations are laid out and they can take it away. They can work ahead. They don't have to follow. They can always work. You have deadlines, but you can always work ahead. So this gives you an idea of what it would look like. So the first page for this module tells you what the purpose of this module is, what are the expected outcomes from this specific piece, and then it says, go ahead and click on next, and you move into the next piece. And step one, watch this video. I leave my video on for this so they can see the slides as well as me talking, because I often, those who've had me for class know about the flexible I-beam I carry everywhere. And so I'm often modeling things with that. And I just, to put a human face on this. It's kind of funny because when you teach asynchronously, you don't see the students. And so I'll be out to dinner or something, and someone will come up and say, hi, are you Dr. Shocker? I'm in your class, or I took your class a couple years ago. That's really fun. Feel free to do that if you've had me for class. I love it. These videos range from like 10 to 20, maximum 30 minutes. And they're chunked out so that you have a little breaks. You can pause, you can do whatever. What I hear from students is that it's pretty engaging. So I would liken it to watching a cool Discovery Channel, maybe not so slick, but my version of a Discovery Channel episode on different types of structures, the people behind them, what's going on in society at the time. So this tells you watch the video, pause when you need to, and then I provide my slides as a handout so that people can go back and study for the exam. This would be the second video in that series. So this one, those two videos and the associated materials would take you through a week. So each module is about a week. And this talks about the final construction of the bridge. You go in from there, and I'll talk to you about how I do my grading in this course right after this, but you have a kind of a low stakes quiz that just tests that you watch the video and that you've moved forward, and that you feel comfortable whether you need to go back again and see that you got all the details or not. So, basic questions. Who contributed to the design of Brooklyn Bridge? If you've watched the video, you should have picked that up. The answer is John Washington and Emily Roebling. So Roebling, John, is the one often credited. He actually died before the bridge was completed. And his son Washington and his wife Emily had major parts in this. Washington also was not able to go to site after a while. And Emily, and this is in the late 1800s, Emily was on site with the construction crew many days and bringing that back and talking to Washington, who was also an engineer. So John died from tetanus. He was on site with Washington one day, and they were on a dock and a boat crushed his toe and he had that amputated and then eventually died of tetanus. So Emily actually did a lot of the work on this bridge, making it happen. So going down to the construction site in 1880, in the 1880s as Emily Roebling is a huge deal. That was still a huge deal when I was in school, to be honest. And this is part of this really cool people story behind the Brooklyn Bridge, as well as talking about what that did for New York City, what the landscape looked at the time. That's the kind of thing you would have as you go through this topic. And then it tells you, okay, you're done with the module now. And the next module is going to talk about Washington Monument and Eiffel Tower. Mark everything is done and you are free to move on. All right, so here's an interesting part of this course. And this is something that I've evolved as a teacher. I was a kind of student who did all my work on time, liked I understood the point grabbing system and how to get an A. I understood that really well. And so it benefited me. I have matured over the years to really understand what the difference is between a grade and learning. And if we look at assessment, AKA often the question, what do I have to do to get an A in this class? It's not the right question, first of all, but the simple answer is you need to learn something and retain it. Um, this is an interesting class because you could come into this class with a lot more knowledge about parts of the subject than other people. But I hope you wouldn't take the class if you don't have anything to learn by it. So people are coming from very different backgrounds. My goal is for you to learn and retain that knowledge, which means if you start at a certain spot, that you leave the class with additional information and knowledge from the class. You all may start at different spots, but you're all going to leave with a delta or a difference in that knowledge and retain that over time. I do what many people do in their classes called scaffolding. So the quizzes that you take are low stakes. Those are for practice because we're still learning. It doesn't need to be high stakes when we're learning. I want you to watch the videos, take notes, understand what's happening, take the quiz, and you find out, I got it. I think I can move on. Or, wow, I didn't get those right. What happened here? And that means that you go ahead and you take the quiz again. So in this particular class, you can take those low stakes quizzes multiple times over, there's a time when it closes, but multiple times. So you go back and improve and learn and repeat. And different people take longer or shorter to do that than other people do. Those quizzes, so I don't have a TA or a grader or any help for this class by choice. This is how I've set it up. So those quizzes, I program those in so that when you get the wrong answer, it'll say, give you some information. It'll respond to you. If you get the right answer, it'll say, yeah, and it might say, yes, and here's why this is right. So that you can learn during that process and without impacting your grade, right? So if you do the work and you take the time, you will get that portion of the grade. The summative is what happens after you've gone through several modules. There's a test, and that one is a one-time test. It's timed, and it looks a lot more like your typical type of exam, Now, an interesting part about this class is at this level, I have much more emphasis on formative. So 60% of this class is formative. That means if you're someone who's gotten away with just showing up, you're really smart and you're good at tests and you take the test and you don't do any of the homework, but you still pass because the tests are worth so much, you will fail this class. And we have people, I warn multiple times when I intro this class, I warn people about this, but that's the difference. Now, in my graduate level classes, that is a different weight than it would be in this introduction class. So one of the questions on my survey for the students is, grading equals learning. Is that true or false? 68% of the students believe that that is a false statement. Grading is not necessarily learning. Okay, so I'm just reporting the results, but it's important because I know there's a temptation from us as professors that grades are, and students, we as a society have taught people that grades are really important. I know that after I smoothed this type of assessment, if I look on my electronic system where I can see how much time people have spent on things, the time that people spend on the videos and not just guessing on quizzes and taking the time in my course has gone up since I went through this, which is the opposite of what most people would assume. Just a couple other pieces that you might be interested in. So this was, now, how many of you, if you teach a class, I had 620 kids in this class, or sorry, 619 in this class. Every student took this quiz. All right, low stakes quizzes are a safe way to learn the material, 99%. My grade should reflect how much I learned instead of how much I already knew coming into the class, 87%. In most classes, this is telling, in most classes, I'm more likely to take a safe project that I already know more about than one that might be more challenging because I don't want to risk messing up my grade, 85%. That's teaching the wrong thing. This is just an overall, and I don't prep them for this quiz, by the way. This is something they take at the end along with their teaching surveys and just ask them. And I just say, I'm interested in what you think of this method. And you can be pessimistic and say, well, they just like it because if they do all the work, they get a decent grade. And they actually have to learn the material to do well in the summative pieces. You were able to take these quizzes many times. And this basically, the 92% of the class said this was a low stress way for me to learn and reinforce the material that was important. And you'll see some other questions. I learned more this way than if I'd been focused on high stakes quizzes with one try. I worry less about the background that others have coming into the class. All right. So it's kind of an interesting sample. All right. Let's talk about the content of this course. Um, this course is designed so that we go through physical understanding of the big structural forms, historical perspective on how we got there, and then a visual experience with structures as art. And this, of course, is Stonehenge. How we get from Stonehenge to something like this in Japan. This used to be the longest bridge main span in the world. There's one longer in Hungary or Turkey now. But how do we get from there to here? Well, we have structures in nature that we replicate. You can see the honeycomb pattern. You can see various structures that some of them very intricate. And then we have man-made structures, sometimes based on those types of things. I'm not going to go through and tell you what all these are. If you're in the class, you will see each of these and we'll talk about them. We talk about major structural forms, everything from columns and arches and trusses to shells and domes. And I'm just going to kind of flick through a couple of these. So here's some columns. And in the course, so I'm going to flick through these. In the course, we spend time going through these structural forms. And these forms I'm going to show you are in order of kind of how complex they are. So a column takes only compression or squishing, I guess is the best way to say it. The column on the far right is in the Leibovitz School of Business and Economics. And you'd say, well, that's a concrete column. What could we possibly learn about that? We could talk about how it serves as a battery to store the sunlight and the heat, energy, and makes that building more energy efficient just by the structure. All kinds of good stuff there. Arches. Arches also are compression. So if you've been to a science museum, a lot of times they'll have an arch you can make with blocks, and the compression in the arch handles that. So all the early materials like stone doesn't do well when you try to pull it apart or shear it or put it in tension, but it's great in compression, very, very strong. And so that's why this is a Pont du Gard, it's a Roman aqueduct in France on the top. This is how you see a lot of arch forms in the older styles. They also happen to be beautiful, so we continue to see them. Cables are the opposite. They take all tension, all pull. They're very effective by pulling. Try to compress a cable, it turns into a wet noodle, basically. So top is a suspension bridge. Bottom left is a cable stayed bridge. The bottom right is a ribbon structure. Okay, might be scary for those of you who don't like heights. But they are all based on these big tension carrying members, whether that's the big suspension cable or the direct cables to the roadway or the ribbon that is holding up basically in tension, this reverse arch looking structure. Trusses are the next step. So trusses are, no matter how complex, something like a cable stay bridge or a suspension bridge looks, if I'm looking at the primary tension component, that part is, the cable part is simple because it's just tension. Trusses are made up of tension and compression members, so some of each, and they work together to take bending. Then beams are more complex because they take all those different things, including flexure or bending, right? So there's all different kinds of beams. Cantilevers, in other words, diving boards, are a specific type of beam where we've got tension on the top, compression on the bottom, and it's a favorite of architects. Shells are very complex, so they kind of work with a whole membrane. Now, these shells are all concrete, very thin concrete shells, so really amazing what can be done here. Domes is a specialized version, so the Pantheon, upper left or upper right, sorry. Superdome, of course, I talk with the students about the Superdome on the left is after Hurricane Katrina. So we got the structural piece. We also have the materials piece. And what I do in this class is I walk through time. I go from, Stonehenge. I quickly move into a discussion on timber and stone, quickly into iron, and then we start looking at the more modern evolution. So we're following time. We're jumping at different spots around the world, and we're developing our different structural shapes by touching on key structures. Maybe not the most famous, we have plenty of famous ones, but these are ones that have a story to tell about the person who designed them, the time period, the location, and the societal impact. And so as I move through time, I have these materials developing, I have the structural forms developing based on what the materials can handle, and I start to see a great evolution here. For instance, we start out just past the Industrial Revolution. I used to be using stone and wood. Now, all of a sudden, I have iron. Okay, iron as a metal is a game changer for what I can do with my structures and how big I can span. So Stonehenge doesn't span very far. Some of the iron structures do. I have a change in power source from animals and humans to steam engine. So I've also got bigger load demands for bridges and things like this. I start to open up my experience. I'm not just looking at a mile around where I live. I'm starting to connect cities at this point. I go from iron to steel, which is an alloy, and I start to get properties like more ductility or more ability to stretch and be flexible and not fail instantaneously. Some really important properties. I start to put steel inside of concrete so that it takes both tension and compression well. I then start to use the steel almost like a steel rubber band. So it actively is compressing the concrete and I get longer and longer spans. This is my specialty area in pre-stress concrete. So if I'm taking this as an engineer in design, this is a graduate class or a senior class. But if I'm talking about it conceptually, I can talk about it in this type of base level class. New materials. So there's composites, there's new low CO2 type cements, there's 3D printing. And the question is, what's going to stay? Has staying power? What's a fad? What's maybe not as practical at full scale? Now, there's consequences when we move and we have progress. There's also an inherent risk in that. This is the Quebec Bridge from 1907. As it was nearing completion, it completely collapsed, killing 88 people. There were two failures actually during this time. It took 30 years to complete. The lives lost here were the construction crew. Many structural failures happen during construction. It's one of the hardest, most unknowns of the load during that time. The reason this one is really important is this is the first time we knew enough and had engineering background to not just do trial and error. We knew how to do calculations, and the calculations, they forgot to include a change that meant this bridge couldn't hold its own weight, right? So this was a calculation error. The myth is, and it turns out it's a myth, although I like this story, the myth is that the first engineering rings were made from this bridge. So we have a ring ceremony where our graduating engineers get a metal ring to wear on the pinky finger of their writing hand, which is supposed to remind you about the importance of the life safety piece of our profession. All right, so the modern structural engineer, we have a lot of tools at our disposal. We aren't doing just trial and error. We have calculations that we are taught that we can predict performance. Ideally, we have field experience to start looking at new and innovative construction processes. And we have imagination to start looking at new forms. The original structural artists went from imitating things that worked, slowly improving on those, trying it out, to innovation, and finally become inspiring. Okay, so it's a whole process, and it's as much of an art form in many cases as it is just what you might think of as Dilbert and the pencil pushing engineer. One of the things I cover a lot in this class is the art of structural design. It means it's efficient, it's economic, and it's elegant. So it's not all about the looks because it should have form and function. And so we talk a lot about when we evaluate a structure, all three of these. I'm going to just give you I'm going to wrap up here soon, but I want to give you a real quick sample of a bridge that might be covered in our class and how I talk about the social and other aspects here. This is the Firth of Forth Bridge. It's kind of a little bit of a heavy duty one in Scotland. If you're ever there, this is a great one to visit. There's a cable stay bridge right next to it. So it's a pretty cool area. This shows you how I would introduce this to the students. So we would have gone through all these other bridges, and you can see I'm hopping back and forth from what's happening on this timeline in the United States with Roebling. And I'm also looking at many other bridges that are around in England and France. Most of these are in England and France. So this particular lecture, I talk both about the Eads Bridge in St. Louis, and I talk about the Firth of Forth Bridge, which is a 1,700-foot main span in the late 1800s by Baker. Briefly, one of the things that influenced what that bridge, so this bridge, really hefty looking thing, pretty unique. What influences that bridge? Well, it wasn't just that it came out of the blue. That Firth of Tay, where this bridge is, there was a disaster in 1879, completely wiped out the bridge. When you have a bridge failure, let's talk about the Baltimore Bridge, for instance, the bridge in Baltimore that was hit. You will know that that next bridge, whatever it is going to look pretty strong, and it's going to stronger than it probably needs to be honest, because public opinion is that's scary, like a bridge could fall down. So here's what we get when we take that extreme. Now, this particular view is really massive. From the side, it looks a bit better. Oh, and I said it's next to a cable stay. It's a suspension bridge. You can see it in the background. So here's the Firth of Forth Bridge. So just briefly, the scientific piece I'm going to show you. The social piece is really in response to what the public needs to feel safe to continue to cross this passageway. And then there's a symbolic piece with the virtual perspectives. If I look at the picture I have here, it's a very different view. If I look at it completely side on, it is a fairly elegant and more slender looking bridge. Without going into detail, some of the structural pieces you might find is that's the Eiffel Tower on the right there on its side. It gets wind load. This bridge, the edge spans look a lot like an Eiffel Tower on their side. And instead of wind load, this is our weight from the cars or the trains or its own self weight. And it follows the stresses that are in the bridge. So this obviously is something that takes a lot longer to explain, but this is something we'd go through in the class. And I at this point would have already talked about this with the Eiffel Tower. This is that scientific piece. This is a really unique bridge. And when Baker was trying to show this to people to make them confident about how this would work, he had a demo with a couple guys who sat there and were able to suspend the middle guy because it is, without going into this, the forces going up have to equal the forces going down. And the main span is completely supported by those two edge spans in a way that is very efficient and effective. Okay, I'm going to wrap up because we need to have some time for questions. I'll leave with a quote by Hardy Cross, who is an engineer. Strength is essential, but otherwise unimportant. So when we think about this, this is a real piece of the artistic, the social, the economic, all the impacts we have in structures beyond just the fact that they're safe and they stand up. So I'm going to exit the share screen here so that we can do some Q&A, and I'll pop back on video. All right.
Thank you, Andrea. So now is the time to take questions. If you do have questions that you would like answered, please feel free to use the Q&A button at the bottom of your screen. Otherwise, we had some questions submitted in advance, so we'll start with those, and we'll see how many we can get through. So I think what we'll start with is if you could discuss useful fatigue lifespan of various materials such as steel, aluminum, carbon fiber.
So we're getting in the weeds here right away. Yeah, so fatigue, given the audience, I'm going to keep this real basic, but fatigue is as simple as if you took a paper clip and you bend it back and forth and it finally breaks, right? I'm not changing the load, but I'm over and over doing that repetitive. So that's the fatigue. In general, Materials. So if I look at a bridge, bridges have more fatigue load because I've got cars driving back and forth. There's a cycle to that. And we design our materials so that they are able to take, say, 1,000,000 cycles where we aren't worried about that fatigue load, but we have to design for a little bit lower load based on a certain number of cycles over the life of that structure. Something like steel, which is really flexible overall, it's all relatively speaking, has more fatigue. If I have a concrete bridge, fatigue typically doesn't control because it's so stiff that that rarely becomes an issue. So that's kind of the summary of how we deal with fatigue. Composites, if you've got a material that's pretty flexible, it really can take, you'll end up with more of that fatigue being a potential issue. And the way we do it is you have material testing and you'd look at whatever that material is and how many cycles it can take and how that reduces its load carrying capacity. That's it.
So talking about materials, I know you'd mentioned kind of the evolution of different types of materials, and there was a question, more of a comment that came in, just with the new materials that are constantly being added, how does that impact your course?
So this course, I add things as we go, and I'm about to do another overhaul of this summer before fall. This course is focused really on the historical piece, but as we add, it does. So I do each time add a little bit more. So I'm talking a little bit more about, let's say, sustainable, resilient materials, the green aspects, the environmental, the CO2. I'm talking more about some of the 3D printing that's coming online. And giving students the tools to say, these are the things to think about and to watch out for. So I work a lot in sustainability and resiliency of concrete. And there are a lot of magic solutions out there. And people love to send me articles on the latest cool thing MIT did that is probably just lab scale. So to replace concrete, for instance, that's the second most used material after water in the whole world. The sheer amount of it, most things that are in pilot stage at this point wouldn't even last a day. Or we're using a waste product and say, oh, there's so much, recycled glass or whatever. The reality is the volume we use, there's not a material that's going to replace that overnight. And so those are the types of questions I ask of a new material to determine if it's feasible.
Okay, and we have some questions about specific structures. One about the Duluth Lift Bridge. I'm wondering if you know, why was the original bridge changed?
Yeah, I think it's more in that case. So the original bridge, there was a little trolley thing that took you across. And I think the change is primarily to have that lift span. They added the lift span, which allowed a much faster, so you can get more cars across. So as much as you don't want to be bridged and have to sit there for a half an hour if you live on Park Point, the fact is that's a lot faster than if you had to get on the little trolley and ride across every time. So it's really an evolution, which it happens, right? So with bridges, we don't, it's not always that they're worn out and that's why we change or replace them, but they've exceeded the traffic has exceeded the capacity of what the bridge can handle.
So speaking of bridges over water, bodies of water, could you talk a little bit about how the beams are secured to the floor of rivers or oceans or other bodies?
Oh, yeah. So those are the piers or the columns, and then the beams sit on that. The beams are typically the roadway for the bridge. So that's really a foundation question. So whether it's on land or water, it still has to be tapped into something that will support it, right? So if I look at something, actually the story is really interesting for both the Brooklyn Bridge and the Eads Bridge because they had to build massive caissons. In other words, they built little structures that kept and then pump the water out so that they could go down and drill until you hit bedrock or go far enough with friction that there was something to actually support that. So it's supporting a lot of load. It's a great question. That particular one, the workers started getting sick. Emily would report this back. The workers were getting sick because they were basically getting the bends. They were so far under, and they would have to take. In the meantime, Eads in St. Louis was making sure that his workers were slowly decompressioning because he had been a scuba or had been a diver at one point. but he didn't share that information with Roebling because they were competitors. Well, ethics is one of the things we also talk about there. But yeah, so you can drive what are called piles into the ground and that either hit the rock below or that they friction. There's enough that holds it, but it's very similar to what we do like for your deck or anything else. It's just underwater.
So we had a question about more of kind of the structure of your course, and this person is wondering how this specific course fits into the larger engineering curriculum that's part of the program.
Yeah, it's a great question too. I think most of our structural or civil engineers do take the course. I I am not under the illusion that everybody takes this course just because of the great knowledge. Part of the popularity is that it covers their liberal education requirements. At the same time, I love that people take a course that covers those requirements and then enjoy it and are really getting something out of it. So in the curriculum, it really is not an engineering course. It covers liberal education, humanities, and global topics, but it gives people a taste of engineering. So this is not even required in the civil engineering curriculum. This is an option for anybody who wants to kind of broaden their horizon in that area, but it does count for some of their requirements. I will get the questions, say, from the Twin Cities campus sometimes. It's like the student wants to count this course as one of their civil engineering electives, and that's not the intent. And so it's not that. It's coming from a different perspective.
And these last few questions are a little more personal. So you had mentioned in a good way. So you had mentioned early on in the presentation about why you're teaching this class. Can you share a little bit about why or how you got into engineering, and then also the transition to teaching?
Oh yeah, absolutely. So my story is not the traditional why I got into engineering. So I went to a high school in the Ozarks of Missouri, and we'll just say that I was not encouraged to pursue math and some of those things. In fact, my advisor said, uh, girls, I was like, what can I do with math? I heard about this thing called engineering, and basically the response was, girls don't do that. That's not proper. And that's why I'm an engineer. So no joke. I guess I was shy back then, but I had an early obstinate streak. And so I decided that I was A, capable of doing it because I knew I was the best student in my math and science courses. And B, that, I was going to show them. Now, it turned out well for me because I really like it and I really enjoy what I do with engineering. Kind of on a personal note, without oversharing, I'm adopted and I fairly recently was able to get connected with my birth parents, and nearly everyone's an engineer or a mathematician. So I guess it wasn't totally random that I decided to be stubborn and do that. But yeah, that's how I started in it. And for me, when I'm talking to students about this, particularly as a structural engineer, so I started out, I was going to do aerospace. I mean, if you're going to show someone up, be a rocket scientist, right? So I started in aerospace. And as I took the actual courses, I realized that I really was attracted to things like buildings that are attached, that don't move, but that are public structures and have, like, I can see things. I have helped design some bridges and I've worked on many projects. And it's really cool to be able to say, I had a hand in doing that. That's the part that really draws me to this and that I think really resonates with some of our students.
Perfect. And the last question, it's an easy one, hopefully easier than the last one. Do you have a favorite structure and why?
So this is funny because because of what I do, I am really careful not to have, like, if I go out in public and give a presentation to an engineering group, I'm really careful not to have a structure that's like to favor one designer or contractor or whatever. So all of mine are like old stone bridges. Um, I really like the bridges of someone who's named Christian Men. who was a Swiss engineer. He does a lot of concrete, pre-stressed concrete bridges. So he's got, if you just MENN, if you Google that, you can find some of his bridges. I've seen several in person. One is the Ganter Bridge, and one is the Suniberg Bridge. And so those are kind of some of my favorites. It changes from time to time. There's so many new things coming out there. What I don't like are flashy bridges that are overly expensive, don't meet the needs, that have construction delays and cost overruns. I don't care what it looks like. Those do not appeal to me.
So maybe you can share with us a little secret. Are there any local bridges in Duluth or in Minnesota that you've worked on that if any one of us were to we could think of you?
So I actually worked for the company on my sabbatical that did the I-35 replacement after the bridge failed. I didn't work on that exact bridge, but I worked on several very similar bridges when I worked with them. There's one in Pennsylvania, in Pittsburgh, the Allegheny River crossing. I have, so a lot of times I'm a consultant when something goes wrong. And so I recently was doing a very large bridge between Hong Kong and China, where I literally walked to China inside of a bridge. The Stillwater Bridge is also a segmental concrete bridge of the kind that I do. I didn't design that, but when we went on site there, I actually have trained a bunch of the guys who did some of the construction process there that I met when I was on site. So I've been really fortunate. The Oakland Bay Bridge, did some consulting work on that. Quite a few around the country. So I'm not, in fairness, I'm not the one sitting there at the design firm going through all the pieces, but I have a specialty area in a certain type of bridge. The segmental bridges are typically huge signature type bridges. And so I get a chance to work on some really neat stuff.
Well, you're an amazing woman, and I know you have lots of former students on the call today that you've made a big impact on. So thank you so much for taking the time to share with us about this incredible course. And for those of you that this is your first Bulldogs Behind the Scenes, our office Alumni Relations hosts these about every month, and we cover various topics. So if you're not on our email list, you can certainly email our office, alumni@d.umn.edu, and we'll get you on that. So again, thank you so much, Dr. Shocker. We appreciate your time, and we appreciate all of you for joining us today. Thanks so much.
Thanks, everybody.